Hi, Chris Good here, and here's another practice t-test. This one's from More Practice T-Test number 3. It's available on the iCollege website. In this one, this is the one we did in class. A researcher hypothesized that electrical stimulation of the lateral habenula, that's brain region involved in motivation and food intake, will result in a decrease in food intake, in this case chocolate chips, in rats. Rats undergo stereotactic surgery and an electrode is implanted in the right lateral habenula. Following a 10-day recovery period, rats kept at 80% body weight, so they're motivated. They're tested for the number of chocolate chips consumed during a 10-minute period of time, both with and without electrical stimulation. Testing conditions are counterbalanced. That's important in repeated measures design, because these are the same rats that are being either stimulated or not stimulated, and they're measuring the number of chips eaten while they were being stimulated versus while they were not being stimulated, and again, counterbalancing the order in which the stimulation occurs. So, compute the appropriate t-test for the data provided below. It's going to be a repeated measures related samples t-test, which means we're looking at difference scores. That's step 1 is to compute our difference scores, and we can subtract. Doesn't matter which one you do, as long as you do it in the same direction and you remember what it means. So, difference scores we subtract. I'm going to do stimulation minus no stimulation, and just if you copy and paste that, it'll do it in the same direction for each one of these. We're going to compute a mean difference score for this set of difference scores by taking the average of all of those difference scores that we get. And it's this number that we're really interested in, so I'm going to bold it and fix it. The average difference score is 1. That's the average difference score. So we're going to use null hypothesis significance testing to answer this question, which means we need to state a null hypothesis. The sample mean difference score is 1. But we hypothesize that stimulation doesn't do anything. So in the population mean difference score, which we write mu sub d, is going to be equal to 0. Okay, that's it for the null hypothesis. We're not worried about means of each one of these groups. We're worried about just the population mean difference score, and we're going to compare our sample mean difference score to it. So we're going to do, let's see, a standard two-tailed t-test, two-tailed t-test, with an alpha of 0.05, and we're going to look up t-crit at, we got to compute degrees of freedom, so let's go ahead and do that right now. We've got the mean. I want to do the n. That's just the count of all of these. I know there's 10 because there's 10 rats. And then there's going to be degrees of freedom is just the n minus 1, right? And it's the number of difference scores that we're interested in here. So now we can look up our t-crit for 9 degrees of freedom. And I'm not going to make this mistake. It's plus or minus. What is the number? Let's go to our t-table. So with 9 degrees of freedom, if we were doing a one-tailed test, we'd stop here and look at the proportion in one tail of 0.05. But here we're going to look at the proportion in two tails combined because it's two-tailed. So 9 degrees of freedom, alpha 0.05, two-tailed test, 2.262. 2.262. All right, now it's time to compute t. That's always, and that's always step number 3. In order to get t, right, we actually need the estimated standard error of the mean difference score, and in order to get that, we need the variance of the mean difference scores, the variance of the difference scores around the mean difference score, and in order to get that, we need the sum of the squared deviations of the difference scores. So we'll start by computing deviations of each difference score from the mean difference score. Deviations are not difference scores. Deviations are deviations of each score from the mean difference score. And I want it to always be that mean difference score. So I'm using the dollar signs to make a static reference. And we'll calculate that deviation for each one. Then we're going to square all of those deviations. That's just this deviation of the difference score from the mean difference score squared. And then here we can sum those squared deviations from the mean difference score. And now we can compute variance. Variance is always sum of squares over degrees of freedom. And now we can calculate the estimated standard error, the mean difference score, as the square root of the variance divided by n. All right, there's our estimated standard error, the mean difference score, and that dropped to a lowercase d for autocorrect, but I really do want it to be subscripted, m subscript large d. T then is going to simply equal the mean difference score divided by the estimated standard error, and there's our value for t. If you're not a fan of decimals, you can actually reduce the number of decimals visible to you if it really, really bothers you, and then you can round to 2 or 3 decimals. Let's compare this t with the critical value. If we go back to the graph here, that 2.262 would be negative 2.262, positive 2.262. Our observed t-value of 1.316 lies here, then, between 0 and 2.262. And so, once again, our decision, I'm going to write it down here so I can get my sentence going across, is to fail to reject or retain the null hypothesis. So here's my sentence. Retain the null is not part of my sentence, but here's my interpretation. We did not detect a significant effect of lateral habenula stimulation on the number of chocolate chips, yummy, consumed. I might want to put something in there about compared with no stimulation, just so that the reader knows what the control condition is. But the sentence isn't over until we include our t with 9 degrees of freedom value, 1.316, and the p-value, which, because it's in the body here, and the shaded regions are 0.05, you know that the body contains an area under the curve that is greater than 0.05. So p is greater than 0.05. Period, to end the sentence, and we're done with number 3. Stay tuned for number 4.